Welcome. In this session in linear data analysis, we'll explore how we can project a vector to a one-dimensional subspace. Let's suppose that we are given a basis vector A, and we're also given a new vector which we'll write as C, and we want the vector in the vector space of that vector A that is, and we'll put this in quotes, that is nearest to C. And we'll define this concept of nearest geometrically, and then we'll see what that works out in linear algebra. So we'll say that the nearest vector, so this nearest vector is, we'll write that as P. And we'll say P is defined as some multiple of A. And why is that? Well, A is a basis vector, and the vector space that it describes are all scalar multiples. So if we want P to be nearest to this space, that means it has to be a multiple of A. So it has to be A, and then there has to be some scalar W that is a multiple of A, and that's the P. So the concept that we have is we'll work from the error vector, is use the error vector. This is a powerful concept in a lot of data analysis, where what we do is we form an error vector and then we try to minimize the magnitude of that error vector. So we'll call that error vector E, and we will define that as being the difference between the new vector C and the projection vector P that is a multiple of the basis. So the goal here, the goal is minimize the error. And to do this, it will be useful if we draw a simple diagram. Let's suppose that we're given a vector A. So this is the origin, and suppose that we're given a vector A like this. And then suppose that we're given a new vector which is our vector C. And the question is, what multiple of A is closest to C? Well, if we draw a perpendicular between C and A, it will look something like this. So that's perpendicular or orthogonal, and this will be our error vector E. And that implies that P will be this. So these are the constraints that we have. We're given a basis vector A and a new vector C. And what we want to do is minimize E. Now, you can see that if we move this from less than a perpendicular, if we move it inward, the magnitude of E will be greater. And if we move E outward, the magnitude of E will be greater. So there is some weight W that multiplies A and causes P to be such that E is perpendicular. And that is the insight that we need. So let's write this as we require the vector A to be perpendicular to the vector E. And that's a geometrical statement. How can we put that in in linear algebra? Well, we could write this in a number of ways. We could write this by saying one way that we write vectors being orthogonal is that their dot product is 0. So we could write A dot E equals 0. And in many previous sessions, we've often found it useful to replace the dot product with the transpose. So that is equivalent to saying that A transpose E equals 0. Well, where does that get us? Well, let's substitute. What is E? E is defined as C minus P. So that has to be equivalent to A transpose times C minus P equals 0. And I could then distribute this, so that's equivalent to saying A transpose C minus A transpose P has to be 0. One thing I was taught was, when possible, put an unknown on the left side and the known values on the right side. So what is known and what's unknown? Well, here we know A and we know C and we don't know P yet. So I'll do that. So if I took that over to the other side, well, my convention for writing that is that AP equals A transpose P equals A transpose C. And what is P? Well, P by definition is a multiple of A. Let's refer back to our diagram here. What we're saying is that P is some multiple of A, and that's really what we're trying to find here. We're really trying to find that multiple W. So that is equivalent to saying that A transpose times W times A, because P is W times A, equals A transpose C. Well, by the law of a vector and a scalar commute, so that's equivalent to saying that W, that's equivalent to saying that W times A transpose A equals A transpose C. And that is equivalent. So can I divide through, so A transpose A, that's just A dot A. Is A dot A ever 0? Well, not by our assumption. We're assumed that A is a basis vector, which means it can't be the 0 vector. So that means that A transpose A dot A, has to be non-zero, and that means that I can divide through by it. So that means that I can represent W as A transpose C over A transpose A. And so I've solved for the weight W. And that implies that, the projection vector is P equals W times A. And I could now write that explicitly. Oh, that's just W. That P equals the scalar W times A. And then I can substitute this in, and I could say that that is A transpose C over A transpose A times the vector A. And so I've solved the problem of, given a basis vector A and any new vector C, I can find the magnitude of the new vector. I can rescale A, and I can find the projection vector. So what we've done now is the reverse of everything that we've done previously. Previously, we've always worked within a vector space. Now we're saying, suppose we're given something that's not in a vector space. How can we find the nearest vector in a space to a given vector?